Welcome. In the last lecture, we learnt about Hubble's law of expansion, Hubble's law, which tells us that the galaxies are all moving away from us with the speed that is proportional to the distance. This is what Hubble observed. This is an observed fact which was first noticed by Hubble, that the galaxies are all moving away from us with the speed that is proportional to the distance, and the constant of proportionality h naught is called the Hubble parameter. And it is useful and customary to parameterize the Hubble parameter h naught as 100 h kilometers per second per megaparsec. That is how it is usually parameterized. So current observations seem to indicate that the Hubble parameter has a value 70, which you would represent by saying that the parameter h, so h naught equal to 70, you would say that h is equal to 0.7. So this small h is a dimensionless number that parameterizes the Hubble parameter. In the last lecture, we also learned about the cosmological principle that the universe is homogeneous and isotropic. There is no preferred position, there is no preferred direction in the universe, and then I told you that if you combine these two things, you are led to a model which has no boundaries. So the model is, in the simplest situation, the universe is infinite, the universe can have no boundaries. So the simplest model is that the universe is infinite and it is filled with galaxies. Because the universe around us is also filled with galaxies, and since the universe is homogeneous, the entire universe is filled with galaxies, and the galaxies are all moving away from one another. This was the basic picture. So if you combine these two things, the observational fact that the galaxies are all moving away from us and the theoretical input that we expect the universe to be homogeneous and isotropic, we are led to a model where the universe has no boundaries, it is filled with galaxies, uniformly filled with galaxies, and the galaxies are all moving away from one another. Now this is the model of the expanding universe, and today we are going to learn a little bit about the nature of this expanding universe. So the first thing that I should mention is that it is convenient to introduce a coordinate system called the comoving coordinates. So if you are going to describe the expanding universe, it is convenient to work in a coordinate system called the comoving coordinates. So this is a coordinate system that is fixed to the galaxies. The galaxies, I have told you, are all moving away from one another. So you can think of it like this. Imagine a galaxy sitting at each point of grid point in this graph paper that fills this part of the universe. It is a part of the universe, and there is a galaxy sitting at every grid point, and these galaxies are all moving away from one another. So at a later time the same part of the universe will look like this, the grid spacing has become larger and the separation between the galaxies has increased. This is the basic idea of the expanding universe. So the comoving coordinate system is a coordinate system that is attached to these galaxies. So let me just draw a picture and explain this to you. So let us draw, let me draw a picture. So these are, let us say, this is a small part of that picture and these are 4 galaxies and this is my comoving coordinate x. I denote my comoving coordinate as x. And in this comoving coordinate system, this has a coordinate 0 0, this has 1 0, this is 0 1 and 1 1. Now at a later instant of time what will happen, these 4 things are the 4 galaxies over here, they are more or less uniformly distributed. For convenience I have represented them as being equally distributed at equal intervals. Now just imagine at a later instant of time what will happen is that the separation between these galaxies has increased. So what it looks like is like this. The comoving coordinates of these 4 galaxies continue to remain the same. So this still remains 0 0, this is 1 0, 0 1 and 1 1. The comoving coordinates of these 4 galaxies continues to remain the same, but you can see that the physical coordinate r, so the physical coordinate r has increased, right. The physical coordinate is the actual separation between these galaxies. So we write the physical separation as a of t into x. Okay, here x is the, x refers to the comoving coordinate system, r is the actual physical coordinate, a is something called the scale factor, which actually tells you that whether there is, that the separation is increasing. So these are 2 galaxies, their comoving coordinate remains same. So this is still at x equal to 0 comma 0, x equal to 1 comma 0, it continues to be there. The x coordinate of these galaxies remain fixed as the universe expands. What increases with time is the scale factor a of t. Okay, and the expansion of the universe, the fact that the galaxies are moving apart has gone into this factor function a of t, which is the scale factor. Okay, so let me write these things here. So we have 3 things, we have the comoving coordinates x, we have the scale factor a of t, and we have the physical coordinate r. Physical coordinate or distance. And the relation, again let me just write it here, is r is equal to a t into x. So the galaxies in this coordinate system sit at fixed values of x, they are uniformly distributed in x, and as the universe expands this a of t is keeps on increasing essentially. Okay, so this is the way you this is a convenient coordinate system to describe the expanding universe.
Sir, can't the universe for all like this comoving coordinates, x, the scale factor is changing and the x coordinate is not changing, that means they are following a linear path?
Well, no, who says they are following a linear path?
In this we have this picture then.
Well, why do you, the question is that x is fixed and a is changing, so it follows a linear path. That is not so. A could be some arbitrary function of time. We don't know what time it is, right? What the function of time is. The basic thing is, this is, you have an universe which is homogeneous and isotropic, right? That's what we believe, and you want to also have the universe follow, you want to also incorporate Hubble's law into this picture. So the way to do that is to assume that the galaxies are all moving apart from one another. Okay, so since the universe is homogeneous, the galaxies are uniformly distributed. Okay, so this is a picture. In this picture, just imagine this is just a picture. Okay, don't take it literally. It's a picture. So it's a kind of cartoon. So in this picture, there are galaxies uniformly distributed, and this fills the entire space. Okay, it is isotropic because the galaxies are all moving away from each other without reference to any special direction. Okay, so this is a model which is consistent with Hubble's law and also consistent with homogeneity and isotropy, where the entire universe is filled with galaxies like this and they are all moving away from each other. That is the picture. Okay, so now we can have a coordinate system that is fixed to the galaxies, and the fact that the intergalactic separation is increasing is there in this function a of t. Okay, now let us ask the question. So now we could ask a question that there is an observer sitting over here, and this is a galaxy G at a distance r, physical distance r, a corresponding comoving coordinate x. What is the speed with which this observer will see this galaxy moving? To determine that, we have to just differentiate r. Now as the universe expands, the galaxies sit at fixed x coordinate, their comoving coordinate is fixed. So the velocity of that galaxy is going to be a dot, where a dot refers to the time derivative dA dt, a dot into x. The comoving coordinate does not change with time, and this can be written as a dot by a into r. Right. So you see, this is the Hubble's law, and a is a function of time, so you can identify the Hubble parameter from this. So the Hubble parameter h, which actually now here is a function of time, so you can evaluate it at any time instant. It is related to a dot, it is a dot by a, both of these are functions of time. Okay, so in this picture, in the comoving, if you go over to a comoving coordinate system, the entire expansion has gone into the scale factor, and the Hubble parameter is basically the rate of change of the scale factor divided by the scale factor itself. Okay, and the present value of the Hubble parameter h naught is equal to a dot by a evaluated at t equal to t naught. T naught refers to the present epoch, the value of t at present. Okay, so h naught is the present value of the Hubble parameter. It is the rate of change of the scale factor with divided by a at the present epoch. Okay, so let me again recapitulate what we have done. We have, so I had told you in the last class that we are led to a model where the entire universe is filled with galaxies and they are all moving away from one another. So now we go over to a coordinate system which is also expanding with the galaxy, which is fixed to the galaxies, and the fact that the separation between the galaxies is increasing is gone into this function called the scale factor. Now we write the Hubble we look at the velocity in terms of this model. So the co-moving coordinate of each galaxy does not change as the universe expands, as the galaxies move away from one another. All that changes is the scale factor. So we are led to a relation where the velocity of the galaxy is proportional to the distance into some function of time. This function of time is a dot by a, and comparing this with the Hubble law, we see that we can identify this with the observed fact seen by Hubble. We can identify this with the Hubble parameter, and the present value of the Hubble parameter is the value of this derivative this at the present epoch. Okay, so all that we have done till now is that we have just changed the coordinate system, nothing else. Okay, we have gone over to a coordinate system which is fixed to the galaxies. The galaxies are homogeneously distributed, so I can imagine them to be equally spaced along different directions in the universe. So I have a coordinate system attached to that, and they are all moving away, so the scale factor is increasing with time. And we saw then we can write the Hubble parameter as a dot by a. Let us now determine what this a of t is. What is the functional form of this a of t? We still do not know what that is. So for this, let us take a very simple model. The simplest model that one could adopt is that we have free expansion. There are no forces. Okay, so that is the simplest model which we shall take up now. So this is the model of free expansion. So in this model there are no forces acting on this galaxy, it is moving freely. Okay, the whole universe is expanding like a set of free particles. All the galaxies are moving away from us, and their motion is just like free particles moving away from us. Okay, we have ignored the effect influence of any force. So let us write down the equation of motion for this galaxy. I am the observer sitting here. Let us write down the equation of motion for this galaxy. The equation of motion we all know is d square r dt square is equal to 0 in the absence of any force, and the physical coordinate has been written in terms of the co-moving coordinate, and as the galaxy moves away from us, the co-moving coordinate remains fixed because the coordinate system moves with the galaxy. So all that changes is the scale factor. So this essentially tells us that the second derivative of the scale factor is 0. So we can straight away write down the solution. The solution is a of t is equal to k1 t plus k2. And these k1 and k2 are constants of which you obtain constants of this. They are basically determined by the boundary conditions. They are constants of motion. Okay. Now this k2 is just an additive constant. You see the behavior of a of t. Let us plot a of t. So this is a, this is t, and the solution is a straight line. That is free motion. Particle moves in with a fixed velocity, which is basically what we have done. So it is a straight line, and I am free to place the k2 decides where the straight line will cut the x axis. So it decides where the scale factor becomes 0, and it is most convenient to choose k2 so that the scale factor becomes 0 at t equal to 0. So a equal to 0, we choose the scale factor so that a equal to 0 at t equal to 0, which implies that k2 is 0. So this thing is not there. Okay, so at the time t equal to 0, the scale factor collapses, it becomes 0. Now you see what is the significance of the scale factor becoming 0. The scale factor becoming 0 means that the separation between different galaxies, whatever be the co-moving coordinate, they all are at 0 separation. The entire universe is filled with galaxies, and different galaxies have different co-moving coordinates. So not only I have galaxy here with co-moving coordinate 2 comma 0 and one beyond, etc. But when the scale factor becomes 0, the distance between all of these galaxies is 0, and the entire infinite universe, the separation between any two galaxies in the infinite universe becomes 0. This is a singularity, right. So this is a singularity. So this is a singularity and the singularity was interestingly given a name Big Bang by Fred Hoyle, who did not believe in this expanding in the evolving universe model. So he wanted to make fun of it, but somehow the name stuck. So this is also called the Big Bang. It was given by a person who wanted to basically make fun of this theory, but anyway the name stuck. So this singularity is also called a Big Bang. So it's essentially a singularity. We don't know what happens over there. The density becomes infinite, and we can assume for the time being that the universe started. That's the beginning of the universe. That's the time starts from there. So t is essentially the time t is essentially the time that elapsed since the Big Bang. That is the time that elapsed since the Big Bang, since the epoch when A became 0. This is also called the age of the universe. Age. This is the cosmic age, cosmic time, or the age of the universe. So if you believe that the universe started at the Big Bang, at the singularity, then this is the age of the universe. Okay, t. So the time t here is called the cosmic time. So t is also the cosmic time, and it is the age of the universe. Okay. Now in this model, so we have worked out this model, we have worked out everything in this model. This is a simple model where the universe is expanding freely. For this model, let us see what the Hubble parameter is. What is the Hubble parameter at any instant of time? So how does one calculate the Hubble parameter? To calculate the Hubble parameter, what one has to do is one has to calculate A dot by A. So let us calculate A dot by A. Remember, A is constant k1 into t. So we want to calculate A dot by A. So A dot by A in this freely expanding model is k1 by k1t. So we see that this is 1 by time. This is the Hubble parameter at any epoch. So if you can measure the Hubble, so you see that at any epoch the age of the universe is inverse of the Hubble parameter. Okay, and the present age, so if you can determine the present value of the Hubble parameter, you can determine the present age of the universe. This gives us the age of the universe. 1 by the Hubble parameter gives us the age of the universe in this simple model where the universe is freely expanding freely. Okay, and just to tell you that this makes sense, let us look at the Hubble parameter. The Hubble parameter can be parameterized as 100 h kilometers per second per megaparsec. What is the dimension of h naught? So in the numerator you see we have length by time divided by length again. So the length cancels out, so the Hubble parameter has dimension inverse of time. Right, the Hubble parameter has dimension inverse of time, and this is called the Hubble time. So this time is 1 by h naught is referred to as the Hubble time. And I leave it to you as an assignment to work out what this is in years. So the assignment is determine the Hubble time assuming that h naught is 100 small h kilometers per second per megaparsec, determine this in years. So, determine this in years. How many, what is the Hubble time, what is the age of the universe if it were expanding freely? But we know that the universe is not expanding freely, so this gives you just an estimate, an order of magnitude estimate of the age. It does not give you a real estimate of what you expect the age of the universe to be. Okay, so as we shall see shortly, this the assumption that the universe is freely expanding is not correct. So, you have to also take into account forces acting on the galaxy. Okay, but it does give us some idea of the nature of the expansion and the Big Bang and the Hubble time scale. Okay, so the Hubble time scale gives us an order of magnitude estimate of the age of the universe. Let us now incorporate the effect of gravity, and strictly speaking one should be using the general theory of relativity, but in this course we shall not use the general theory of relativity, we shall use simple Newtonian physics, and let me tell you that the results that we will get will be correct. So, the results match. Okay. So, there is no difference in the results if you were to use the general theory of relativity. So, let me with this prelude, let me get down to calculating the dynamics of the expanding universe. So, we are going to basically study now the dynamics of the expanding universe. So, let us write down the same thing again. So, we have an observer over here. This is the observer, and there is a galaxy here G, and we would like to write down the equation of motion for this galaxy. Let us say that the galaxy has mass m. Now, since the universe is homogeneous and isotropic, the mass distribution, the density of the universe is everywhere the same. So, you can think of it as a spherical mass distribution around the observer because it is isotropic. So, the observer, around this observer, the mass has a spherically symmetric distribution, and it is well known that if you want to calculate the force on a mass which is inside a spherically symmetric mass distribution, then only the mass inside this sphere will contribute to the force, the mass outside will not contribute. Okay. So, we can write down the equation of motion of this galaxy. It is very simple. The only force here is gravity. At these large scales, the only force that acts is gravity, only force which is known is gravity. The universe we assume is charge neutral on large scales. So, there are no net charges, so it is neutral on the average. So, we can then write down the equation of motion for this galaxy. What you have to do is you have to just consider the force due to the mass inside a sphere of radius r. So, this is my galaxy, and the force on this galaxy is due to the mass inside a sphere of radius r, and this, so the equation of motion is quite straightforward. M d square r dt square is equal to, so I can write it as a vector if you wish, or you could write it as a scalar, it does not matter because the forces are all radial, the acceleration too is radial. This is equal to minus g into the mass within the sphere of radius r into the mass of the galaxy divided by r square, or I can write it as divided by r cube into r. So, this is my equation of motion for the galaxy. In the previous example of free expansion, we had ignored the effect of gravity. So gravity here is going to slow down the expansion of the universe, that is the main thing. Okay. Now we can write this in terms of the density of the universe. Remember that the density is the same throughout, because we have assumed that the universe is homogeneous. So if I write this in terms of the density, we know that the mass inside a sphere of radius r is 4/3 pi r cube into rho. Okay. So we have these two equations, and then if we substitute this here, this r cube cancels out from the denominator, and the other point to note is that the mass of the galaxy also does not figure anywhere. This is the equivalence principle. The gravitational acceleration is independent of the mass of the galaxy, that cancels out from the inertial mass, and the gravitational mass are the same. So this cancels out, and it does not depend on the mass of this particular galaxy. So we have then the equation that d square. Okay, further what we could do is we could write this in terms of the co-moving coordinate system and the scale factor. Okay, we will do that in steps. So let us write down this equation first. The equation then becomes d square r dt square is equal to minus 4/3 pi g rho into r. So that is the equation that we have. And this equation can further be further simplified, and we can write, see, this is for a particular galaxy. Now we could write it in terms of the not this, we could write it in terms of the scale factor. So let us replace the physical coordinate in terms of the scale factor into the co-moving coordinate. The co-moving coordinate of the galaxy is fixed, it does not change. So I can take it outside the derivative, and you see that it cancels from both the left and the right hand side. So we are left to an equation for just the scale factor, and the equation is d square r d square a dt square is equal to minus 4/3 pi g rho into a. So this is the equation that governs the evolution of the scale factor. And once you solve, so the point here is, once you solve this equation and get the scale factor, you know how the entire universe is expanding. So by just studying the equation of motion of a single galaxy, you can work out how the entire universe is expanding, because the scale factor is the thing that has the encodes the information about the expansion of the universe. Once I know how a of t evolves, I can use this to determine the motion of any galaxy. Different galaxies correspond to different coordinates. Okay. The other point to note here is that the density of the universe does not vary from place to place, but it does vary with time. Why does it vary with time? Basically the mass is conserved. So as the universe expands, you can see, as the universe expands, the mass inside any volume, physical volume, has to be fixed. So the length, the volume of the universe goes up as a cube, but the mass has to be constant. Mass is density into length cube. So we can see that the density into the scale factor cube has to be a constant, right? As the universe expands, the volume increases as a cube, the mass is conserved, mass within any volume, any region is conserved, mass is neither produced nor destroyed. So in addition to this, we also have rho a cube is constant. As the universe expands, the density goes down as 1 by a cube, and we can write this as the present So this refers to the present, a subscript 0 always refers to the present. So this is the present density into the present value of the scale factor q. And we will use a comoving coordinate system so that it matches with the physical coordinates at present. So the value of the scale factor at present is assumed to be 1. That is how we shall work. So we shall assume that the present value of the scale factor is 1. Okay. So now we have to simultaneously solve these two equations, one equation being the equation over here and the equation over here. So we have to simultaneously solve these two equations. So what we could do is, you see there are two functions of time in this equation, one function of time being the scale factor, other is the density. So what we could do is we could just eliminate density from this whole thing by replacing density by the present value of the density divided by a cube. Okay, so let us do that. So what this equation then becomes is a double dot is equal to minus 4/3 pi g, and we are replacing the density with rho naught by a cube. A naught is 1. So this will be replaced by rho naught divided by a cube, so I will have 1 by a square here. Okay. So what I get here is rho naught a minus 2. And the way to solve this equation is as follows. What you do is you multiply the left hand side and the right hand side of this equation with a dot, so this you can see is a time derivative d by dt of a dot square by 2. If I differentiate a dot square, I will have two terms, one of these terms will be a double dot, the other term will be a dot, so I will get a double dot into a dot, and there will be two such terms, so this 2 will be cancelled out. Okay, and this is so this same equation can be written like this. Now if you look at the right hand side, a to the power minus 2 into a dot, this can be written as 4/3 pi g rho naught into d by dt of 1 by a, because if I differentiate 1 by a, I will get a dot into minus a to the power minus 2. Okay, so this same equation can be written like this, and now I can integrate both the left hand side and the right hand side of this integration, and in doing this integration I will then have to introduce, if I do the integral, I have to introduce a constant of integration. So the solution to this equation is a dot square by 2 is equal to 4/3 pi g rho naught into 1 by a plus a constant of integration e. So the same, now that this is a solution to this equation, where e is a constant of integration that we introduce when we integrate this. Okay, so we have worked out the solution, the first integral of the equation that governs the expansion of the universe, and you have to do one more integral in order to solve this. Now let us just spend a little time and look at this equation. Okay, this equation, if you notice, is essentially the left hand side, the term on the left hand side of this equation is essentially the kinetic energy of the galaxy. Consider a galaxy at unit comoving coordinate. Let us consider a galaxy at a comoving coordinate x equal to 1. Then its velocity will be a dot, and its kinetic energy, let us say its mass is 1, so its velocity is a dot, its kinetic energy is half a dot square. So if I have a galaxy at unit comoving distance and unit mass, then its velocity, its kinetic energy is half a dot square. Similarly, let us look at the potential energy of that same galaxy. So the potential energy of a galaxy here is going to be minus gm by r, and for a galaxy at unit comoving coordinate, the mass inside is 4/3 pi into the volume into the density. The density inside is rho naught, okay, is rho naught, sorry, it's rho, which can be written as for rho naught, which can be written as so the density inside, so the mass of this is, so the mass inside here is pi 4/3. So let us just look at the mass inside this. The mass inside this is here 4/3 pi r cube rho. R cube for a unit comoving coordinate is basically a cube into rho. A cube into rho can be written as rho naught. Okay, so the mass inside this sphere is 4/3 pi a cube rho naught, basically 4/3 pi rho naught, and the potential energy is the mass divided by the distance minus mass times the distance. So this is the potential energy. Okay, so this is essentially the kinetic energy K or T plus the potential energy. This equation essentially same as this. Okay, so this is the, and this E is a constant. Okay, so this E can be thought of as being the energy of the galaxy which we are discussing, which is conserved in the motion. Here it appears as a constant of integration when I do the first integral. Okay, now the question is how to determine the value of this E from observations. I have a universe, I am living in a universe, and how will I determine, to integrate this equation once more and determine the solution for the scale factor, I have to determine the value of E. The whole thing depends on the value of E. How to determine the value of this E? Okay, to determine the value, so let us discuss that. So to determine the value of E, let me write down the same equation in a slightly different way. Let us put back the value of the density over here. So rho naught is rho into a cube. If I put back the value of the density over here, this becomes rho into a cube by a, so rho into a square. So if I put back the value of the density over here, this equation then reads a dot square minus 8 by 3 pi g rho a square is equal to 2e. So I have multiplied that equation by 2 and I have replaced rho naught as rho into a cube. Now let me divide this equation by a square throughout. So if I divide this equation by a square throughout, what I get is 1 by a square here. This a square is gone and I have a square here. Okay. So this is the equation that we have. Now look at this equation carefully. This equation essentially reads that the value of the Hubble parameter at any instant of time, because A dot by A is the Hubble parameter, this is the square of the Hubble parameter, is equal to minus 8/3 pi g rho is equal to this constant 2e by A square. Okay, this is the general equation. If you apply this equation at present, so we want to determine the value of E from present day observations. To do that, what you do then, you apply this equation at present, t equal to t naught. At t equal to t naught, this becomes h naught squared. So at present what we get is h naught squared, and I can take h naught square common over here on the left hand side. Then I have 1 minus rho divided by 3 h naught square by 8 pi g is equal to 2e rho naught. So if I apply this equation to the present epoch means t equal to t naught, then this becomes the present value of the Hubble parameter, this becomes the present density, and this becomes A naught, which is 1, which we have chosen to be 1. So we have this equation. Now the point to note here is that in this equation we have this quantity over here in the ratio of these two quantities, which has to be compared to 1. Okay. So the first thing that you can see here is that this combination 3 h naught square by 8 pi g is something that is of dimension of density. Okay, and this is called the critical density. So the present value of the critical density, so this is rho c naught this is called the critical density. So another homework, determine the value of the critical density, right? You know the value of h naught and the others are all known. So determine the value of the critical density of the universe. Okay, the critical density is a very crucial density scale in the universe. So the ratio of the, so if you look at this expression, it is h naught square into 1 minus the ratio of the actual density now, rho naught, that is the actual density of the universe now, to the critical density now. This is what determines the constant E, okay, of integration, constant of integration E. So 2E, and this ratio is given a name, it is very important in cosmology, it is given a special name for this, there is a special name for this. So this is the ratio that occurs over here, it is denoted by omega naught, it is called the density parameter. And the equation, the constant E is now can be written in the following way, the constant E okay. So let me again remind you what these things that we have discussed are. We see that the Hubble parameter defines a density scale in the universe. So the present value of the Hubble parameter defines the present value of the critical density, which is rho c naught, and the critical density is 3 times the Hubble parameter square by 8 pi g. So this is at present, at any instant of time you can write down the critical density rho c as 3 h square by 8 pi g. This is true at any time instant, not only at the present but at any time instant, any instant of time. Okay. Now, so the Hubble parameter measures defines the density scale, and the ratio of the actual density of the universe to the critical density is called the density parameter of the universe, omega, and its present value. So this omega can also be defined at any instant of time. So omega at any instant of time is equal to rho these are all actually functions of time, possibly functions, because h also is a function of time. So the critical density is a function of time, and the density parameter also is a function of time. We are interested here in the present day values. So the present day value of the density parameter omega naught is the value of the actual density of the universe to the critical density of the universe. Okay. Now what is the speciality of this ratio, density parameter? The value of the density parameter decides the value of the constant of integration E. If the density parameter has value 1, this implies that the constant of integration is 0. Okay, this is the critical value. It divides between two different kinds of cosmological models. Okay, if omega naught is less than 1, it implies that the constant of integration is greater than 0. If omega naught is greater than 1, it implies that the constant of integration E is less than 0. And this constant of integration E, I told you, can be thought of as being the energy, total energy of this galaxy. Let me end today's lecture over here. In tomorrow's lecture, we shall interpret what the significance of these and then look at some of the solutions.
Critical density is also a function of time.
Yeah, it could be, right? It's a function of time. Why not?
Critical density is 3 h naught square by 8.
That is the present value of the critical density, h naught square. But h is a function of time, so the critical density is also a function of time. Okay. Any other questions?